PCM system. In the last two classes, we discussed PCM system with its block diagram for transmitter, channel, and receiver. In the transmitter block diagram, the first important operation we do is sampling, and for the sampling process, one of the important conditions we need to consider is at what rate we need to do sampling. Particularly, the sampling rate must be slightly greater than Nyquist rate, where Nyquist rate Fs is equals to or greater than 2W, and W is called as highest frequency of the message signal or bandwidth of the message signal. Bandwidth of the message signal. So that is the only important condition or the important parameter we need to consider in the sampling block or sampling process. So otherwise it creates the rising effect. That's the information we need to include for sampling process. The next is quantization. We know in the starting part of this module 5, we discussed about the quantization process and the significance of quantization. Once again, we will try to elaborate the quantization process, but by considering non-uniform quantizer, because what we already discussed is a uniform quantization process, which is very simple and it is not preferred practical purpose, and practically we do quantization almost by using non-uniform quantizer. So that's what, after understanding the quantization process by using uniform quantizer, so now we'll move to a non-uniform quantizer as a part of explanation of the quantization process in the PCM system transmitter block diagram. And after understanding the non-uniform quantizer, which is very important, the today's topic is because once we use the word quantization, by default it is a non-uniform quantization, because non-uniform quantization is bit less simple and less complex and less practically preferred. So uniform quantizer, non-uniform quantizer is in practice or in certain applications, it is preferable to use a non-uniform quantizer. So we start with what is the definition of non-uniform quantizer, then how we apply, when we apply non-uniform quantization, after that what are the important mechanisms we do for the implementation of non-uniform quantization, particularly it is in the form of compression and expansion, and collectively it is called as compressor and expander. So generally, totally the operation is called as compander, compressor, expander. The mixing of these two, compander, is always preferred in quantization process. I will take an input m of t, I will do the compression of it, and then I will do uniform quantization, and I encode it and I transmit it. Other side, as I am doing a compression at the transmitter side, so to make back reverse operation we do at the receiver side is called as expander. So by doing compression, it is possible to do a compression of the signal which is totally very in a huge manner, and so that I can use a uniform quantization. Non-uniform quantization is equals to compression plus uniform quantization. So I'll explain you later. Okay. Anyway, after understanding the concepts of non-uniform quantization, basically there are two methods of the two laws are used to implement non-uniform quantization. One is called as mu law, another is called as A law. So the compression laws, A law and mu law, are used in two different domains, or in the two different standards. One is used in European standard, another one is used in American standard. But both are the part of PCM system, where PCM is used for telecommunication department for the purpose of voice transmission. Okay. So it starts with say reading non-uniform quantizer. As the title is an explanation of quantization only. We are dealing with the second block of third block of PCM system, which is a quantization process. In that quantization process, basically, and one thing I want to make clear now, already we discussed in one module sampling process, and last module almost is related to the quantization process. What is the ultimate conclusion of sampling process? That is the module 4. And next operation is quantization, and which is a module 5. So ultimately what I am getting, the output of the sampling process, input of the sampling process, input of the quantization process, and output of the quantization process. And next, what actually we are doing with encoding is also very important. So just now I want to concentrate on the two important statements which gives you a clear picture of this sampling process and the quantization process, and hence it is giving you a digitization of analog signals. Then we will move to the non-uniform quantizer. Okay. Basically, you know, a sampling process, it takes input what? M of t. A sampling process takes input of the sampler, takes input M of t, and it gives output M of NTS. So that I'll take this block as sampling process. Okay, what I'm giving input? Analog or continuous M of t. So what I'm getting output of this? Yes, we need to do sampling at the rate of equal or greater than previous rate. That is there. You think how you want to do a sampling process or how you want to implement this process is left to you. But anyway, by implementing the sampling process in a practical way means what? Fs must be greater than or equal to 2W. With this condition, if I do sampling, actually what I am getting output is M of NTS. What the M of NTS it is? Symbolically it represents sample value. Symbolically it represents sample value, or basically it is a discrete signal. Basically it is a discrete sample values. Discrete means in which parameter? Because your signal is having time versus amplitude. Your M of t is having what? Basically it is analog. My M of t is looking like this. It is having a continuous amplitude with respect to time. See, amplitude is continuous, time is continuous. Everywhere it is having its own value of amplitude. So this is my M of t. Then what is this M of NTS basically? How I get that M of NTS? My M of t NTS is going to be look like so. Direct delta functions at a given instance of times. This is the signal what I am getting output of this quantization sampling process. Then what actually it is? Yes, diagrammatically I have shown it. What is the name we assign to the signal? It is discrete sample values, which is discontinuous in time. Because I am defining exactly at 1 TS, 2 TS, 3 TS, n TS. When in n is an integer, your M of t at 1 TS, M of t at 2 TS. So that's what I am making time as discontinuous. Here it is continuous, here it is discontinuous. At that instant I am measuring the amplitude, whereas my amplitude is continuous. But I made time as discontinuous or the discrete. So that means the output of the sampling process is discrete time signal. It is a discrete time, but amplitudes are continuous. Because I have not defined anything about the amplitudes. I defined only with respect to time. You take the signal amplitude at 1 TS, at 2 TS. So I made time as a discrete. That's what it is called as discrete in time. The samples are discrete signal. They are the discrete signals. in the form of time discrete. Okay, next is I use quantization. So what I am doing actually with this quantization? After understanding the quantization, after discussing the quantization, nearly 2 to 3 classes we discussed. Along with the quantization wise, let it be. Quantization wise is a mathematical analysis about the performance. So now, with respect to this concepts of the quantization, what output I am going to get? What output I am going to get? And how it is going to be present diagrammatically is also very important. So what I am getting output, first of all, what I am doing in this quantization process so that I can take its output. So what I am doing in the quantization process, there are the discrete levels of amplitudes. There are the discrete levels of amplitudes, and the samples are quantized to map to one of the nearest quantization level. Nearest quantization. For example, therefore, I taken 0 to 20 volts, sorry, minus 10 to plus 10 volts is my input m of t. This is what minus 10, and this amplitude is plus 10. Then I divide these levels, sorry, the total voltage range of minus 10 to plus 10 or 20 volts into 20 levels. If I divide it into 20 levels, each level is equals to 1 volts. 20 by 20 is equals to 1. 1 volts will be there. So 0 is the one level, next is the one level, 2 volts, 3 volts, 4 volts up to 10 volts. Total 10 levels at positive side. Similarly, 10 levels at negative side. So you take a sample value. If the sample value is 7.2, then it will be approximated to 7 volts because it is very near to the quantization level 7, which is equal to 7 volts. The sample value is minus 2 volts, then it will be related to the quantization voltage of 2 volts because my quantization is having a level 2 minus 2 volts. Minus 2 is there, plus 2 is there because every 1 volts is there. Any value we can map to, any value we can map to a nearest quantization level. So in this way, these all levels, for example, if I take this is a quantization level and next quantization level and the next quantization level like this. See, as this quantization level is very near to these three samples and these three samples are represented by level 1, 1, 2, 3, 4, L4. The voltage value is left to you. So these three samples are represented by level 4. Not by the sample value, by the quantization level. They are approximating to the quantization levels. So now what I am getting, this sample values are converted into this voltage levels. So what I am getting output look like okay. The sample values are there. Sample values they are now available in the form of the signal will be these are the levels I am using to represent my signal. See the changes, you observe the change between these two. Actually, the status is not there. Simply it is what? A sample value it is. The signals are moved like this. No status is there. This is what the signal will represent input of the quantizer and output of the quantizer will look like this. What is now? The now is the now output is in the form of what? Amplitudes are also now discrete. Here it is what? Continuous because sample value 7.2 is also there. Even if I take the low sample value 7.3 is also there. 7.4 is also there. If I take the samples with less time durations, every value is there. Sample values are there for every instant. The output now what I am getting, it is now available in the form of a one level. So amplitude is discrete. Now the amplitude is discrete. Quantizer makes amplitude discrete. Sampler makes time discrete. And input of the quantizer is time discrete continuous amplitude. The quantizer will do what? Amplitude discrete. So that output what I am getting is called as discrete in time and discrete in amplitude, which is called, anybody? What is the name for this signal? Which is discrete in time and discrete in amplitude? Anybody? So please one of you try to answer it. Nikhil? Nikhil Naik? So if the signal is discrete in time, discrete in amplitude, it is called as what? I think it is studied in DSP. Prerana? If the signal is discrete in time and discrete in amplitude. So I think you are outside. Okay. So any other students? Rachana Shettar? Rachana Shettar? Rachana Kulkarni?
Yes, sir.
So what the answer you expect if the signal is discrete in time and amplitude? Okay. So mute it. No problem. It is called as digital. It's called as digital. So that means, can I call the staircase as a digital? No, yet it is not, because it is not in the form of digital, it is in the form of staircase. Next operation is what? This staircase is further applied to encoder. This staircase is further applied to encoder. So that I am going for next encoding operation. So what I am doing encoding operation, when I give a sample, maybe it is 1.2 volts. If the when I do the sampling at a particular instant, the sample value is 1.2 volts. So the next is that sample value will be quantized. That 1.2 will be mapped to what? 1 volts. That 1 volts will be encoded. I am assuming that 1 volts will be encoded by 8-bit encoder, and I am doing in the form of sign, because minus is auxiliary in my signal and amplitude is minus as well as negative. So I can encode in the form of what? Sign magnitude format, where first bit is representing sign, second bit is representing, the remaining bits are representing the magnitude. That's what, as it is 1 volts, I can write this plus 1 volts, plus means 0 and 1 means 1, 2, 3, 4, 5, 6, 7. So 8 bit is totally, it is an encoder output. So available in the form of what? 0, 0, 0, 0, 0, 0, 1, 2, 3, 4, 5, 6, 7, and it is 1. This is what the signal generated by the encoder for the input m of t, doing sample rate at 1 ts with the sample value of 1.2 volts. The quantization will take that 1.2 and it will be converted into a quantization level as 1 volts, because 1.2 is very near to 1 volts. So that 1 volts will be encoded by what? Number 1. So code I am giving plus 1 volts, 1 level plus 1 volts, second level plus 2, similarly minus 1, minus 2, minus 3, total 20 levels are there with sign minus 10 to plus 10, the 20 levels. So each level is encoded by their corresponding number by using sign magnitude concept. Therefore, I am using this bit for sign. It indicates plus, and this is for magnitude. Total value of this output is 1. So plus 1 volts. The symbol is generated like this. I think now that topic PCM system, particularly what signal I will be giving for each block and what that each block will do and what it gives as output for next stage. So what is the next stage operation and its output, finally what I get. It is about the PCM system. Now I want to back to on non-uniform quantization because just now I briefly revised the information what we discussed in the last 2-3 classes, or even though I included something about the module 1, module 4 and the module 5 starting portion. I briefly reviewed it. So once again, please try to concentrate what output and inputs are available for each block is very important. What we know theory, beyond that what practical things are available is also very important. Okay. So non-uniform quantizer. Is it clear? Sampling makes signal in time discrete. It converts the signal into discrete in time. Sampling will do it. Makes the continuous signal into discrete in time. Quantizer will do the signal discrete in amplitude. So quantizer input is what? Sampling output. Sampling output is what? Discrete in time. So first of all, quantizer input is already discrete in time. Quantizer will do discrete in amplitude. Ultimately, output of the quantizer is discrete in time as well as amplitude. So staircase I am getting at output. This staircase levels will be further encoded by the encoders. So with that encoding operation, perfectly I get signals in the form of 0, 1, 0, 1, or electrically it is in the form of plus volts, minus volts, or plus volt, 0 volt. Okay. The non-uniform quantizer. So please concentrate and try to understand because it's the practically preferred uniform non-uniform quantizer. In certain applications, it is preferable to use a variable delta. So that's what non-uniform means. Uniform means what? Uniform quantizer means step size delta is constant or uniform, same. If the step size of a quantizer is constant or uniform, then that quantizer is called as uniform quantizer. Next is what? Uniform quantizer. Then the non-uniform is delta is variable. Step size is variable. First it may be 1 volt, second the value of the step size may be more than 1 or less than 1 volts. The definition of non-uniform quantizer is delta is variable, where delta is called as step size, where step size is the space between the two different representation levels. Okay, so after understanding the definition of non-uniform quantizer, next we'll move to where we use non-uniform quantizer, under what condition we prefer non-uniform quantizer. Okay, in certain applications it is preferable to use a variable delta. Variable delta means non-uniform quantizer. For example, the range of voltages covered by voice signals. Range of voltages covered by voice signals. Range I am using range. It is from the peaks of loud talk to the weak passages of weak talk. Peaks of one possibility is what? Peaks of range of voltage. Range of voltages. So peaks of loudspeak. Peaks I am using corresponding to loudspeak passages of weak torque. Weak passages of weak torque. When you're talking slowly and you are moving from one word to another word. So when you talk with low pitch, weak torque, in that weak torque, weak passages means what? A transition from one word to another, because there is a gap. When I talk, I am using a word by word pronunciation. There is a transition from one word to another word. In that transition, there is no information to be generated, but there is a sound. That sound is having very weak amplitude. So this peak and weeks are having the range in the form of 1000 to 1. 1000 to 1. Order of the range. The range of voltages is order of 1000 to 1. So I am not writing any voltage, it's order. If the loud torque peak is 1000, then weak passages weak torque is 1. That's the proportionality. So it's not 1000 volts and 1 volts. No, it's not like that. If it is 1000, then weak is going to become 1. That is the ratios between the peaks of loud torque and weak passages of weak torque. So you can show this by, so maybe when you are talking, the voice may be like this. This is what called as peak of loud torque, and is known as passage of weak torque. Try to understand. So it is what very large in amplitude compared to this weak passage of the weak torque, and this is called as peak of loud torque. Because when we talk, sometimes it is very loud, sometimes it is very weak, and again still it is very weak, and the transition from one word to another word takes place. So that is the variation of voltage range for the voice. Okay, so when I do the quantization of this, in this case, what I do, I use, because see, it is very loud increase, a very fast increase, but the information content is, okay. Is it not audible? Okay. So this weak and loud. So in the loud case, only amplitude is very less, but the information content is very less. Your loud means what? You are increasing the pitch, you are increasing the amplitude, but the content is only that word itself. So because of that, you are not increasing the information content, but you are increasing the voice pitch of that information. That's what I want to take this with large and step size. Okay, so this is what I will take step size very large, because I want to cover 1000. Because I want to cover entire 1000 volts. If I take a small size of delta, then I will invest 1000 levels here. But the remaining portion is not having that peak, because occurrence of these peaks are very infrequent. It's not continuously. Sometimes we talk loudly. It's not a continuously 1 hour. So I think in observation of the class, sometimes we talk with loud because of some scolding the students or doing some angry movement or something. Depending upon that, the talk will be having a loud. Loud is means what? The pitch is very high, amplitude is very high. So when I want to do the quantization of this, which is almost in the range of 1000 compared to this one, then I will invest 1000 levels here compared to the big passes where only one is required. But in this case, that weak transitions are there, the information is more. But in this case, the information is very less, amplitude is increasing because of the situation, but the information is almost the same. That's what you cover this range, higher excursion of voltage it is. Higher excursion voltage cover with less number of quantization levels. So if I want to use the less number of levels, then I have to go for large step size. That's what I use a large step size for this portion. I use large step size for the load torque portion, and I use large step size. Means what? Large step size means step size is large means less number of quantization levels. Less number of quantization levels. Okay. So the other possibility is weak passages, which is having a small range of voltage, but lot of information is there, transition period is there. So in this case, I use small step size so that L is large. This is what step size is varying. For this I am using large step size, for the next case I am using small step size. So depending upon the variation of this voice pitch, voice amplitude voltage, so we are selecting the value of delta. See that? Large step size means large delta, small delta. So what actually it is now? Delta is changing depending upon the situation. It is called as non-uniform quantizer. So why I am using non-uniform quantizer? Because here I want to cover voltage varying with a very large value, but the most information is same. Information is same, but because of your loud torque, it is increasing in amplitude. So I don't want to invest unnecessarily more number of quantization levels where that information is very less, but amplitude is very high. In that case, I use less number of quantization levels by using large step size. Next is what? For this, I am using small step size, more number of quantization levels so that every information will be maintained. Weak passages must be protected because they have the informations. A normal voltage it is. Everywhere there is a voltage information distributed. But this is infrequent. If it occurs, better you use a different quantization step so that you can reduce the number of quantization levels. That number of levels can be used at the weak passages because which we need to take care of, which we need to protect. So I can protect this with less or more number of quantization levels with less step size, which I saved with respect to the loud speed. So in this way, here I am using large step size, less number of quantization levels. Here I am using small step size, more number of quantization levels. On and average, it is same as with uniform quantization only. Maybe uniform quantization levels are 20. Here I am using 15. Here I am using 25. So 25 plus 15, average will be what? Again, will be 22. 25 plus 15, 40 divided by 2 is equals to 20. The same I am using. The percentage of quantization performance will be same as uniform quantization. So with this concept, ultimately, in such cases, if the information signals voltage is changing drastically, randomly from large value to small values, so then better to use for non-uniform quantizer so that it's going to give you a better performance. So there is a signal, so there is a concept of under what condition we prefer non-uniform quantizer. It is also very important. Okay. So after understanding the concept, we will discuss what are the different techniques available to do the uniform quantizer implementation. So non-uniform quantizer implementation. Okay. So use of non-uniform quantizer. First, try to understand. Use of non-uniform quantizer is equivalent to. Now we are thinking about implementation of non-uniform quantization. We discussed why to use non-uniform quantizer. First, I defined what is the non-uniform quantizer, where the delta is variable, where the step size delta is variable. It is called as non-uniform quantizer. Then I explained you when we prefer non-uniform quantization, under what condition, under what, for what examples I am using non-uniform quantization, I explained. Next is what, how to implement non-uniform quantization process. Okay. So yeah, I'm explaining about the implementation side. So implementation side means what actually how we are going to implement it. Use of a non-uniform quantization is equivalent to, okay, implementation non-uniform quantization, okay, use of non-uniform quantizer is equivalent. This is very important because if I am using a non-uniform quantizer, basically actually what I am doing is equivalent to passing m of t through a compressor and then applying it to a uniform quantizer. Okay, so this is what the statements are very important. Use of non-uniform quantizer or the implementation of non-uniform quantization is equivalent to passing of the m of t, analog signal m of t, through a compressor. First we pass the given m of t through a compressor, which will compress the signals when there is a loud peaks, compressed state, and then use uniform quantizer. Basically, the uniform quantizer only I am using, but I am using another one device called as a compressor. Before uniform quantization, I do compression of my input m of t. After doing the compression of the input m of t, it's not m of NTS, m of t. So compress it, then do the uniform quantization, which will be called as non-uniform quantization. Okay, so this compression, how we compress the signal, basically there are two laws are there to do the compression of m of t. So one is called as mu law, another one is called as A law. We will discuss those two laws particularly related to the mechanism of compression, because it is not a blind compression. We are not compressing the signals blindly. There is some definition or some mathematical model. Based on that, we are doing the implementation of compression technique. Similarly, expander at the receiver side, it is exactly complementary of the transfer function of this compressor. Opposite process. So I concentrate on mu law. Two compression laws. First one, mu law. Second one, A law. So okay, mu law. It is defined as how you want to make compress. Defined as or defined by modulus of V, output of the quantizer. Modulus of V is equal to log of 1 plus mu by m divided by log of 1 plus mu. M is there. I take M, I operate on M in the form of log, so that I am going to get some output of the quantizer V, which is particularly doing the compression of the signal. The rate of compression is in the form of logarithmic twist. The signal amplitude is small, it is a linear. If the signal amplitude increases, it is going to have its impacts in the form of logarithmic, where it is going to be suppressed or compressed. So it is the one equation we have 47 as per our textbook, where M and V are normalized input and outputs. Mu is a positive constant. Mu is a positive constant. Okay. I'll show you the figure so that it becomes very easy for us to think it mathematically. How that mu law, A law is going to be defined. Zero, 1.0 is normalized values. 0.2, 0.4, 0.6, 0.81 it is normalized. Input M, it is normalized. Output V. Okay. Then this is what the value for mu equal to 0. And when you use mu equals mu is a constant, positive constant. When I take mu equal to 0, say by mu equals to 5, look like this, and mu equals to 100. Is the input versus output of a quantizer with the different values of mu. If it is A law based, this is mu law, and this is for A law. So here it is also a straight line, same numbers because it is a normalization process, and it is going to be a straight line. Then this is almost localized. This is A equal to 0, A equals to 2, A equals to 100. So take this figure A, number is figure 24, and figure 24 B. Okay. So this is a plot for mu law for a different values of mu. For a different values of mu. Okay. For a given value of mu, another important definition. So mu equal to 0 corresponds to what? Mu equal to 0 corresponds to uniform quantizer. In case if you are using non-uniform quantizer, a compression with the technique of mu law, with the method of mu law, if I take mu equal to 0, basically that non-uniform process is going to become uniform quantizer, because when mu is greater than 0, then only there is a compression and hence the non-uniform quantization. If mu equal to 0, no compression, there is no non-uniform quantization, where it is going to become a uniform quantizer. It's very important. mu equal to 0. Such type of questions asked, they may ask in the gate question. Just now usually they ask in the gate questions, they are not asking some mathematical calculations which requires more than 30 minutes or 1 hour. No, they ask the questions which are logically we need to think. If mu equal to 0 in mu law, which is basically it is a non-uniform quantizer. So what is the type of quantization it performs? Basically it performs the uniform quantization itself. So simple, okay? So this is the one important note, or you can take it as a start. Mu equal to 2, mu equal to 5, mu equal to 100, they are comes under the non-uniform quantization only. Maybe a small amount of variations are there, amount of compression techniques, or the compression amount may get changed, but they are all belongs to non-uniform quantization. But the straight line where mu equal to 0 is going to be a part of uniform quantization for a mu law concept. Okay. The next another important concept this one is for a given value of mu, for a given value of mu, the reciprocal reciprocal slope of the compression curve defines the which actually it is a reciprocal defines the slope curve defines the quantization step and is given by derivative of modulus of m with respect to modulus of v. See this what? This definition is very important. Quantization step can be obtained by using compression curve. Reciprocal of compression curve gives you quantization step, which is defined as derivative of modulus of m with respect to modulus of v. Modulus of v is given in equation 47, which defines the compression curve itself. So that means what if I know this, then I can calculate a quantization step which is derivative of modulus of m with respect to modulus of v. So it is what? D modulus of m divided by d modulus of v is equals to, you substitute here, do the differentiation, and finally we get the answer. I think this is going to become, because it is not having any m, I am doing m with respect to v, and it is a constant. Because of that, this constant derivative is going to become constant. It is 1 by this, 1 by v. It's not audible. Okay, see it is 1 by dm by dv. Substituting this in the denominator, it is going to become a numerator, and do this differentiation and you will get the answers. Do that mathematics. It is log of 1 plus mu divided by mu into 1 plus mu by m. I think all is the equation number 48. Okay, so the differentiation of this equation with respect to the denominator, you do the differentiation with respect to given parameter. Finally, you get this answer, which is giving you a quantization step size. Okay, see now this quantization step size look like Neither be a linear nor be a perfectly logarithmic. Strictly it is not a linear. Is it linear? No, because there is a log term. There is a log term, so it is not perfectly linear. Is it perfectly logarithmic? No, because it is also having some other constants here. So because of that, it is neither be a strictly linear nor a strictly logarithmic. So for smaller values of m, for smaller values of m, it is going to look like a linear, or approximately it is going to be a linear. When the values of the m is increasing, it is going to look like, or it is going to behave like a logarithmic. That's one of the important observation. The interpretation from the equation number 48. Okay. So with this, in order to restore, sorry. That's what in. Thus, we see that mu law is neither strictly linear nor strictly logarithmic, but it is approximately linear at low input levels. Approximately linear at low input levels, and approximately it is logarithmic for high input levels. So logarithmic at high level, so that it's going to become complex. Logarithmic behavior. It behaves logarithmically at higher input levels. It becomes linearly at the lower. Linearly means what? One-to-one correspondence. 2 volts mapped to 2 volts. At the higher levels, it is not mapped to as same. It is a logarithmic values are going to be. So in this way, we are going to compress the signal amplitudes. Okay, that is the one of the important mechanism. So another one we use is called as A law. A law is shown in the figure 24b, and only change is the definition of the quantizer output. So it is V equals to A modulus of m divided by 1 plus log A for 0 less than m less than 1 by A and 1 by A less than modulus of m less than 1. So this equation is equal to 1 plus log of A modulus of m divided by 1 plus log A. So it's about 49th equation. Similarly, by doing this operation, we can find the step size, where step size is equal to, that is d modulus of m divided by d modulus of b is equal to 1 plus log A divided by A for 0 to modulus of m less than or equal to 1 by A, and it is equal to 1 plus 1 log A, 1 plus log A into modulus of m for 1 by A modulus of m less than or equal to 1 for the equation number 50. Okay. So in this case, when A equals to, sorry, it is not 1, then it is A equals to 1. When A is equals to 1, the A law is going to perform uniform quantization. When A is greater than 1, it is going to perform a non-uniform quantization. The range of mu from 0 to 100, a range of A from 1 to 100. That's the only difference between both are same. One American standards they are using A law, European standards they are using mu law. Almost if you see the terms, both are look like same. In one is better than other in one or the other ways. So it is only two standards we used for PCM system as a part of telecommunication department, because initially the PSTN public switch telecommunication network implemented with the objective of transmission of voice only. Now over that you are getting implemented in TV and everything. Now it is a multimedia, but initially it was designed with an objective of transmission of voice. And when we want to transmit voice over the public telecommunication network, ultimately we need to do the A to D conversion. At the time of A to D conversion, we use quantization, particularly in the form of non-uniform quantizer, because your voice varies in the a loud torque and weak torque with a different range of voltages, and we prefer non-uniform quantizer. When we go for non-uniform quantizer as a quantization part of A to D conversion, either may be implemented in the form of mu law or may be implemented in the form of A law. One is the US standard and the other one is the American standard. US, European standard and American standard. So it is only with respect to standard we need to adopt. Whether we adopted this or this, anyway it is a part of A to D conversion in the PSTN network, so that it is going to become compatible for the international. See why we use these standards, because that standard is going to define worldwide, and if you adopt it, that is going to be processed by any industrial product or equipments and components. So with this, the quantization process related to non-uniform is complete. Just now I want to explain you another 10 minutes time. Details of regeneration. Already explained you regeneration. Just now I want to give a brief concepts of regeneration with the diagram. So this repetitive regenerators are used in channel. It's used in the channel or over a channel at a different or at an appropriate points. So already explained you. Regenerator repetitive repeaters are used over a channel. Ultimately, the objective of regeneration is to manage the distortions and noise effects over the transmitted signal, because it may get distorted or maybe added with the noise. So, because of that, we may not get the original signal at the receiver side. So, for that purpose, the digital signals are always at an intermediate points over a channel regenerated, repetitive regenerator. So, in that repetitive regenerator, what we are doing, we are totally managing the interference noise effects can be minimized or eliminated almost by using this repetitive regenerator. Basically, a regeneration can be done. Regenerate means what I transmitted signal, same signals will be regenerated at intermediate points over a channel. It is only possible for the digital. That's what most important feature of the any digital system lies in the ability to control the effects of distortions and noise over a transmitted pulse. See, it is what most important feature of any digital system lies in the ability to control the effects of distortion and noise over a transmitted pulse. Yes, it is an inbuilt property of digital system. It can manage noise better than pulse modulation techniques and analog modulation techniques, or analog systems and pulse based systems. Digital system is more. How? Because of the capability of regeneration, which is not there in pulse modulation techniques or analog systems. No, it is not possible. So to try to understand what is the meaning of regeneration, okay? It is the ability to control the effects of distortions and noise over a transmitted pulse. When I transmit a pulse, what happens? After certain distance, it may be changed like this, along with the something noise will be added. So we don't know, it may get distorted by the attenuation, by the noise, by the some other channel impairment mechanisms, so that it may be totally not available to get the information in a easy way. So in that case, we need to go for regeneration. Is the only technique makes to manage the effect of noise and distortion. Okay. This capability is accomplished by reconstructing the signal by means of a chain of regenerative repeaters at appropriate points over a channel. The three basic functions performed by a regenerative repeaters are the three basic functions. Three basic functions by the repetitive regenerators are: first one, equalization, called as, it is because of attenuation purpose. Because of attenuation by channel or noise. Maybe channel attenuates the signal or maybe noise interfere with the signal. So anyway, the amplitude of the signal will get changed. That I will do a equalization process so that the amplitude will become normal. So next point is timing. So timing is what? Because of dispersive nature of the channel. Nature of the channel. Channel dispersion means what? When I transmit a pulse like this pulse is not amplitude over a channel. The amplitude may get changed and decrease, and finally in time duration is a 1 second pulse is maybe greater than 1 second pulse. So I'm getting like this. The spread in time is called as a dispersion. The dispersion is causing the timing mechanism effect. The timing mechanism will get shift, change. So that timing, then decision making. Okay. So what I will explain you. First of all, I am using what? PCM wave distorted. PCM wave equalizer, amplitude equalizer it is. Amplitude equalizer. The output is given to DC, DD, decision device. Then this will be given to a timing circuit. Timing circuit and degenerated pulse. Okay. See amplitude equalizer. So it will take care of the amplitude distortions. After making the amplitude equalization, which is because of the attenuation and generated noise interference, that amplitude will get changed. That will be managed by the amplitude equalizer. After doing that amplitude equalization, so the information of timing circuit can be extracted from the received PCM wave with concept of where SNR is minimum. When SNR is minimum, but signal strength is more compared to the noise. In that case, I know exactly at what point, midpoint of the pulse. So that timing can be given to a timing circuit. The timing circuit will give at what time that received pulse must be sampled. So maybe, so it is going to be equalization will take place like this. Okay, so I want to do the sampling here because there is a one bit here. Sample it. If the sample value is less than threshold value, make it as 0 and again go for the next sample. If the received signal is more than, sample value is more than threshold, generate one and again in the next instant. What instant we need to sample is given by timing circuit. Timing circuit gives the information to the decision device at what time it has to do the sampling of the input. So once you do the sampling at a given instant of time, the sample value will be compared with the threshold. If that value is greater than threshold, it will be decides in favor of 1. If the sample value is less than threshold, decision device will take a decision in favor of 0. So in this way, it is regenerating the distorted PCM wave as if you what a transmitter side. Okay, this is how ideally it is giving you the same signal what you transmitted will be regenerated over a channel by the regenerators. But practically it is not possible to get the same signal what I transmitted. Anyway, there is a delay because after certain amount of time, propagation time, it is going to do that regeneration. So yes, there is a delay. Along with that delay, if this signal if the signal is not giving the correct information, means if by mistakenly if the signal is attenuated in hues such a way that the sample value will be less than threshold, so that it will take decision in favor of 0 even though you transmitted 1. So that may cause error. That may cause error. Actual transmitted is 1. Because of that noise and distortion, that sample value I am getting or decision device will get sample value less than 2.5 volts. Maybe it's getting 2.2 volts. So if you get sample value of 2.2 volts corresponds to bit 1, it will take a decision in favor of 0 but not as a 1. So that is called as a bit error. So that is also one of the possibilities there with this regenerative process. Along with the timing of the pulse is not going to be same as what I transmitted. There is a relative displacement of the timing which takes place, which we call as a jitter. There is a small amount of jitter introduced by the regenerator, and also there is a small amount of error introduced by the regenerator if you are not taking care of design of regenerator in a proper way with respect to its internal circuit and its spacing. So with this, the PCM system information will be completed. I think you know the decoder. Similar to encoder, you get back to the decoder. I am doing encoding what? 8-bit I am doing as a one code for one level. Then at the receiver side, use 8-bit back to one quantization level. This is called as a decoding operation. After decoding, it will be given to a low pass filter. Basically, it's called as a low pass reconstruction filter. With that reconstruction filter, it is possible to get back to the original signal by taking input sample values and using sync function as an interpolation function. With the sync function as an interpolation function, that low pass filter with input sample values, it is possible to get back to the original continuous analog MOP signal at the output of PCM receiver. With this PCM system, along with the transmitter block diagram, channel and receiver completes. In the tomorrow's class, we starts with another one system is called as input version of PCM system is called as delta modulation. Okay.